This is the C.V. Sundaram Memorial Lecture. It will be delivered by Professor Padmanabhan. Before we go ahead with the lecture, let me brief you about Professor Sundaram. Of course, he does not need any introduction, but because we all know about him. But just in case somebody may not be aware of his achievements and his contributions, so I will just go through the presentation in a few minutes. Slides, yes. So Professor C.V. Sundaram started his research career as a student in IISc Bangalore under the supervision of Professor Brahm Prakash. Then he joined the Department of Atomic Energy. He became the head of the Metallurgy Division. Then he took over as the director of IGCAR. Then he was the Homi Bhabha visiting professor at NIAS Bangalore, and then he was honorary visiting professor at NIAS Bangalore. So this is the chronology of his career. Now, more importantly, as we can see from this slide, his contribution has been immense to atomic energy and metallurgical engineering and material science in general. So he was a pioneer in India for the production of the rare and reactive and refractory metals. He made a lot of contributions at the nuclear fuel complex Hyderabad. Then for the FBTR in around 1985, and he was also associated with the fast breeder reactor program of 500 megawatt. Now, other than the contributions, he was also like associated with various professional bodies, and in fact he was the editor of the transactions of IIM, vice president of IIM, president of IIM, and also the president of the Indian Nuclear Society. And it goes without saying, but he was awarded with various honors, which include the National Metallurgists Day, Padma Bhushan, Sanjay Gandhi Award for Science and Technology, Doctor of Science by BHU, Distinguished Material Scientist by MRSI, Homi Bhabha Lifetime Achievement Award, and Lifetime Achievement Award from the Ministry of Steel and Mines. So the achievements were, yes, of course, there were a lot of achievements, and that was primarily because he was a very, very passionate researcher, and of course a very articulate speaker and writer. He nurtured the younger generation and created good talent out of them, and of course, most importantly, he was a very humble and compassionate human being. Now, at the end, let me direct you to the book written by Professor Sundaram, which is Atomic Energy in India 50 Years. With this, let us move to today's lecture, and that is by Professor Padmanabhan, and he will be delivering the Sundaram Memorial Lecture today. Before we go ahead with the lecture, I would request Professor Indradev Samazdar, who is chairing the IIM Mumbai chapter as of now, to kindly introduce the speaker.
Professor Padmanabhan was an alumni of BHU, did his PhD, what used to be called as SED, from University of Cambridge. He had a very distinguished career, starting from being a director of IIT Kanpur to almost all awards in his credit, and more importantly, an excellent and passionate research career. Not only the number of research papers which you are able to see, which is very, very respectable, the patents, the technology transfer, but Professor Padmanabhan's name is always going to be related to subjects like superplasticity, ring boundary sliding, the basis of the whole page, and so on. So all students of physical and mechanical metallurgy get to learn Professor Padmanabhan's thing. I'll keep my this thing short. It's a great honor to have Professor Padmanabhan among us. Now I leave the stage to Professor Padmanabhan.
Very good evening, or afternoon, how you want to phrase, 5 o'clock, to the chairman of the meet, Indradev Samadar of long-standing friendship, Mukhopadhyay, young friend of more recent origin, respected audience, it is my great pleasure to be delivering the C.V. Sundaram Memorial Lecture 2021, not only because it is an honor bestowed on me by the Indian Institute of Metals Mumbai chapter, but because it is in memory of probably one of the finest human beings I have come across in my life. Not coming. Yeah. Yeah. You see, as a teacher, as someone who has been a teacher all my life, I will start with a quiz. What is common among the following? Zirconium plant at the nuclear fuel complex in Hyderabad, the hafnium production unit at the nuclear complex again in Hyderabad, titanium sponge production plant in Chavara near Kollam, and FBTR going critical in IGCAR. Commonality is C.V. Sundaram. The first three are based on the flow sheets that were developed by Mr. Sundaram and his research team. And the fourth one, the reactor has been there for a while, but it went critical only after Mr. Sundaram decided to go in for carbide fuel. And this way, I mean, in four succinct points, I can bring out the kind of enormous contribution he made to this country. But you see, he was not only a great metallurgist, but also equally comfortable in metaphysics, Carnatic music, and English literary criticism, and above all, a great human being who displayed Spartan simplicity. His life was his message. Here was a man, when comes such another. It has been a great privilege for me to have been associated with him since 1972 September till his demise in 2008. So over the years, I looked upon him as my conscience keeper, and some of the very good pieces of advice I received from him, which I cherish to this day, are as follows. You have no control over what happens to you, but you can always be in control of how you react to a situation. The mind should always be the master of the body. I would like you to develop values which are beyond the self, beyond the present, and beyond this life. Mahatma Gandhi had three goals in his life: eradication of poverty, removal of untouchability, and Hindu-Muslim unity. All three are still today a vexing problems. Therefore, will you think that he lived in vain? As former President Radhakrishnan said, let us be guided by the distant stars, not by dim streetlights. This lecture is dedicated to the immortal memory of Mr. C.V. Sundaram. I have chosen for today's talk ICME, that is Integrated Computational Materials Engineering, a paradigm shift in materials design to manufacture. This paper or this presentation is co-authored by Dr. B.P. Gautam, who heads the ICME program at TCS, and Gerald Tennyson, who is one of his deputies. But many youngsters have helped us at different specific problems in this whole picture. And also, I would like to thank two organizations, Tata Steel, both Tata Steel Jamshedpur and Tata Steel Holland, and also their R&D wing, which is ABSTC, Aditya Birla Science and Technology Center. Without their supply of data, the models which I will be talking about would not be there at all. As they say, data is today's oil, and therefore we are deeply indebted to these two organizations which have helped us as our partners in this program which I am going to talk about. But then before that, we would like to say a few words about how ICME has to be viewed when you are looking at it for an industrial application. Before that, what is the need for modeling? I mean, you see, for example, an industry fellow in IIT Kanpur, for example, Professor Sudhir Jain, present director of IIT Gandhinagar, when he ran a course, he said, this course will be run without even a single equation. So this is the way industry looks at all these equations and analysis and so on. Therefore, what is the need for ICME? I will elucidate it with a simple problem from Kapitsa. Kapitsa, as you know, is the man who studied the structure of liquid helium-2, won the Nobel Prize for that. And he posed a simple problem in combinatorics. Supposing you have got enough number of modern typewriters, which usually have about 40 characters. And suppose you also have enough monkeys which can punch the keys but cannot read any of the characters. How many monkeys will you need to get the first line of Shakespeare's Hamlet correct? What is that first line of Shakespeare's Hamlet? It is just who is there. Who is there is just 10 characteristics. If you solve this problem in combinatorics, you will get an answer that the number of monkeys you require will be 10 to the power of 39, which is more than the number of atoms present in this universe. This is the danger of random, undirected thinking. Of course, always we say tukka lagya and all that, but at the same time, it is tremendous luck you need in order to get it right if you do some random thinking. And in addition, many studies have revealed that return on investment on modeling and simulations work, it varies anywhere from 10 to 1 under the best condition to 3 to 1 under not so excellent condition. So now you see, I come to the topic. What are the challenges? You see, as metallurgists or material scientists, we should think of our good past also. 1960s and 1970s, or even starting from 1950s, 60s and 70s, until the first man landed on the moon. The growth at the upper end of the high temperature, you see, for example, the Carnot cycle is the limit, and therefore, development of a field like metallurgy is evaluated in terms of the highest possible operating temperature in a, let us say, ultrasonic plane. The supersonic plane, for example, has to operate at a very high temperatures. Therefore, per year, the maximum temperature that could be operated upon went on increasing at the rate of 17 degrees per year. This progress, of course, stagnated after the moon landing because funding became questionable. I mean, in other words, there was drastic cut in funds and so on. And but then, mechanical engineering was the early days, the laggards. But then, they moved forward, and then, they came in with digital engineering. Digital manufacturing revolutionized the field. For example, those of us who are on the wrong side of 50 know that from 1940s till about 1991, when the economy got liberalized, we only had the Ambassador car. But in the early 90s, in just 2 years, Tata Motors came up with 4 models. All these were possible because of the digital manufacturing that the mechanical engineers achieved. And then, they went into life cycle management, that is cradle to grave. You start with the raw material coming in till the end of the product. But then, they went one step further. Now they talk about cradle to cradle because, recycling also is there. Therefore, it was realized somewhere in the beginning of this millennium that materials are now the laggards. So that means we have to accelerate material development and its exploitation in industry. So this is the driving force for this whole development. And what are the problems we have in materials and product design? It's time consuming. You require experts who are in short supply, and you require enormous experimentation. They have to be reduced. Process design and scale up, of course, this is very expensive also, because as you know, a lab scale operation, when it goes to a pilot plant, it gets multiplied by 10 times and it becomes 100 times more if you want to do it on a industrial scale. The process design and scale up, very expensive setup, large number of trials. Again, you go only by trial and error. And in addition to that, you have got the operations. And in operations, there are two things. One is the uncertainty. Uncertainty, the predictability is less, is mainly because incoming raw materials may change its quality, suppliers change, and therefore the product input qualities change and so on. And then again, the plants also need a lot of advisors and experts. I mean, again, this is very difficult. People are elsewhere. For them to come on time to help you also is a problem. Time is also a constraint. So all these things have necessitated us to think about the lacuna in product and process development. Therefore, you can say there is a need for acceleration, optimization, and cost reduction. And whole plant has to be integrated. I mean, for example, if you make some mistake in the casting stage, that can reflect in the final roll sheet that comes out. So, and in addition to that, a lot of developments have taken place in computer science. We should take advantage of it. Computational methods, that is, a lot of modeling work is going on. And again, a lot of data are collected in the laboratory and in the plant. And these are underutilized. So that means if we overcome the key challenges, that is, reduce the dependence on experts, and again, have a proper depository so that we don't go on repeating. Once you capture the process knowledge, how do you systematically use it? And then also identify those processes which are repetitive, boring. They have to be automated so that they become less burden for the human beings involved. And digital tools have to be promoted in industry. I mean, often one of the things we find in our plants is when some controls are put, people just remove it so that there is no bother about the checking of the quality and so on. So that should be discouraged. And also, most importantly, as I said, connection of all the units in a particular plant will have to be done through the use of platforms or systems that will facilitate integrated processing. And you see, this also is something familiar to metallurgists. When you process a material, its structure changes. When the structure changes, the properties change. When the properties change to the level that you want. And again, mechanical engineers have been dominating the field, and therefore they have been only doing the one which I have shown here in the first portion. That is, this is mainly based on AGMA codes, various kinds of but there is not much kind of basic scientific thinking going on here. And here, cost effect analysis or goal-oriented design have been the main job done. But then, with the arrival of material, we are able to start at quantum mechanical level to molecular dynamics. From there, you go to microstructure, that will what is known as the mesoscopic scale. And then, go to continuum mechanics and so on. So the result is very integrated. The scientific thinking becomes very powerful. But here there is some uncertainty because these are in early stages. So therefore, the concept of materials, integrated engineering was generated. That means materials, manufacturing processes, and component design. They were all integrated together into the thinking mode much before the component is fabricated. And they are integrated into a holistic systems. For example, if you look at this figure, you have product development, knowledge base is there. It can come through the web, that is, the data available in the web, or you will have design interfaces like experts and handbooks and codes and so on. And then, you have also, when you have a particular case, you have knowledge for solving that problem, you have knowledges and rules, you have uncertainty methods, you have cost models, and you have also, can you remove this? You have also manufacture databases, and you have when you have models where when you do a processing, material structure changes, that interrelationship in terms of models, and then you can also have models with which correlate structure to properties. So all these things are framed together, and in addition to that, personnel. For example, designer should be interacting with plant engineer. Otherwise, you may end up by designing something which cannot be manufactured. So therefore, this was the concept which has come very successfully. And many books have been published, books, proceedings, conferences, proceedings, and journals, and so on. And most of them in foreign countries, but it is not as though there is nothing there. IIM has brought out a few volumes, and of course, quite a bit of activity is started in this country in more recent times. 4 famous case studies I would like to highlight here before I go to what we want to say. Here, for example, Boeing, when they decided to introduce composites in their Dreamliner, they in fact had this accelerated insertion of materials program, where in fact, the total time of this much was reduced practically to half the value. So the time of development and insertion in industry reduced by nearly 50%. So this is a famous example. Another one is what Ford came up with. This is the virtual casting for, let us say, an engine block. This is the kind of a procedure they adopted. They gave the alloy composition and the product property requirements, and then, concentrated on the mold, casting, and the heat treatment in terms of modeling. And then everything is satisfied, means you proceed to predict the local microstructure. If that is also successful, you predict the local properties. And again, you also, in the casting, what is the kind of residual stresses there? So that means now your casting is ready. Then, you apply the loads which have to be carried by this component. And then, you predict the service life. And when it is acceptable level, your product is in. It took them 10 years to do that. But at the same time, that was the first major success which drew the attention of the United States government, and also they came up with ICME papers and all that through the National Science Academy, National Engineering Academy, and so on. And this is a famous work done in Germany at hydroaluminium in Bonn by Jürgen Hirsch and his colleagues. They in fact came up with the sheet metal rolling in aluminium alloy, aluminium, magnesium, manganese alloy, for example. And here, of course, the main thing is you identify time and the temperature are important in the preheating stage. And then, when you go to rolling, time, strain, and strain rate. And then also, when you come to coiling, time and temperature. Cold rolling will involve temperature, strain rate, and the stress. And annealing, where temperature and time are involved. All these things are identified. Yeah, total kind of a picture is involved. Everything is integrated. The knowledge gained in first step is transferred to the second, and so on. And similarly, what is there in fourth will be known to the first one or first step also. And therefore, you are able to predict everything. You end up by producing the microstructure, the faces present, the inclusions, the textures, and also what happens to the texture when you give, a cold rolling or subsequently annealing. So this is a very famous work. And also Timken, they came up with a kind of a complete ICME picture for seamless tube making. Here, of course, you know the procedure. That is first piercing, expansion, induction furnace temperature equalization, and then multiple stage rolling, and then finally sizing is done through rotary swaging. And afterwards, you can either air cool it or slow cool it. So these are the famous ones which we like to cite as examples. But then when you look at the whole picture of ICME, you see, where it can all be used. Development of new materials. The moment you identify new materials and the need is established, you can think of applications, benefit, time of need, performance requirements, and properties and product. Similarly, when you go to development, who will do it, where it will be done, or who will own the intellectual property, funding, all these issues have to be sorted out. And then, you start exploring. Here is where ICME will be computational modeling will be very powerful, because I need not try only one composition. I can try several compositions because everything is being in silico, that is done in the computer. So therefore, it is not like doing an experiment on different materials over a very long period of time. And exploration of candidate systems, of course, you can use methods like Taguchi and so on to do the experiments very optimally. And you optimize the properties based on physical principles. Chemistry is frozen and process is outlined. And then, comes the most expensive part, which is process scale-up. Because something is done in the lab doesn't mean it will work in industry. So you have to go to intermediate stage of a pilot plant or to the final product. And this, you see, is achieved full-scale production and performance validation, whether the fabrication characteristics you assumed works, etc., they have to be done. And again, another very large, expensive component would be design availables. So that means, I want to produce a product. So it has got a shape, it has got a geometry, and therefore, whether in full scale you try to make it and make sure whether it is viable, possible, and then, have all the properties, static and dynamic properties, and fatigue, and ductile to brittle transition, corrosion, specific, etc. So all these things can be simulated also, in which case you will move much faster. And supplier qualification is probably the simplest step. You will have to identify the parts from where it will come, and market and contract prices will be there. Production preparation will have to be worked out. And then, you have earlier, you in the experimental route, you will have fabrication and destructive testing. And finally, in-service support. That means once you have sold your product, you will have to support it till the end. So that means you have to take into account environmental effect, load and thermal fatigue, and damage, and also quality issues which will come once in a while, and then you refer back to the plan and so on, and repair and refurbishment, and life extension sometimes will be in critical components will be asked for. You will have to do that. So all these things, if I sum up, it takes anywhere between 15 to 20 years. This is a picture we have taken from IBM. IBM talks about this for 15 years. But most of the other places, it takes about 20 years. So that means by replacing many of these experimental things by modeling, you want to bring it down by 50%. That is the goal. And again, here also we can apply what is known as supply chain concept. So that means you don't have to develop everything yourself. But ultimately, as I have pointed out here in the first column, you have to have all these. Except for customer approval, everything you should be capable of doing it finally if you are producing a product. But on the other hand, model development, for example, if you are a company, you can always involve academics. And similarly, if you have model integration into engineering software, you can involve a technological company. Supposing you want to integrate it into a system, then you will have to have a corporate company. For example, Aditya Birla, for example, involved TCS. Similarly, Tata Steel involved TCS. So therefore, this is the other things. So therefore, I can use the supply chain concept provided you are confident that the partners will not lead to delay in your system. So this is the concept which makes life simpler, because, as they often say, you should only concentrate on your core strength and core technological requirements, get other things supplied by others. For example, ISRO is a successful organization because right at the beginning, Professor Satish Dhawan said, what can be done others will not be done in-house. So this kind of a concept, supply chain concept, will be very useful in ICME also. And in India, right now, of course, many institutions are attempting it. I'm sorry that I'm not mentioning all of them. The major ones which are showing some very positive activity right now is the national hub of ICME at IIT Kanpur, which is co-funded by IIT Kanpur and TCS. And the Computational Materials Lab of IIT Madras, IISc Bangalore, IIT Bombay, and of course, there is a very strong group in DRDO, particularly DMRL. And now ICME, you see, is as I said, industry dislikes too much of analysis, because as they often say, too much analysis becomes paralysis. So therefore, if you want to produce quickly, you shouldn't think too much. So therefore, if you want to convince the industry people to use ICME, it has to be purpose driven. So that means reduce product and process development time, reduce laboratory and plant experiments and trials, and quickly troubleshoot for product and production and product issues. If you convince them that you can do that, they will say, go about it. But on the other hand, at the end of which, we will have to give them into a simple thing, that is, press this button. If it's okay, press this button to change. This knob you twiddle to get the right value. So these are all the instructions we will have to reduce it to. Therefore, that is the important thing. And again, you should look for a solution that is fairly accurate. Don't bother too much about this accuracy. And but all these questions which are raised above, they should be answered by taking the realities of the plant, that is the uncertainty of the plant, into account. And again, integration and engineering as important as modeling of materials. And again, once I have developed all these models, they have to be industrialized and democratized. What do I mean by that? That means something, your control development in the lab, that has to be scaled up to laboratory. You have to identify the places where which you will maintain the centers, where, at what are the parameters you will control, how they will be controlled, what will be the tuning method, and go, no-go kind of press buttons. So all these things have to be thought out and located. And again, democratize it. That means even the plant operator should be able to implement the final thing, because you see, he is the one who is working in real time. So if there is a change and all your calculations are done and it comes, and if it is okay, he will leave it unchanged. And if it is not okay, he will do the needed adjustments in terms of norms and so on. And again, today, the computer science has advanced so much that models, data, and knowledge you have, they can be very well curated and also maintained and retrieved at the right time that you want. So that means managing information, storing it correctly, and retrieving at the right time, that becomes also a major issue. And this is an example, of course, Tata Steel. That is the so-called dual phase steel. Here, for example, you can see this is the whole kind of integrated picture that you would like to develop. That means, we are starting with liquid steel. The steel making is an oxidizing environment. So sulfur removal cannot be done in the steel melting unit. So you have to remove ladle desulfurization. Similarly, you have to remove gases and so on. So that means secondary steel making is an important thing. And for that, you see thermodynamic modeling of chemistry, control, and then inclusion formation, if inclusion is there. And then multi-phase CFD will have to be used for this in order to achieve the flow and thermal modeling and inclusion dynamics. You see, this is because you have three phases here: liquid metal, slag, and argon that is bubbled through the ladle. So that means it is three-phase flow, and so the CFD becomes a rather tricky business. But before that, if I go one step further, the alloy design is done by density functional theory and molecular dynamics, which of course, would not be of relevance to a steel plant because the alloy is already frozen. And now, finally, if I look at it from the customer requirement, what is it that he or she wants? Strength, ductility, formability, fatigue, and other properties, they should be in the range they want. And you have to develop this model or this chain of models within the limitations of the plant. For example, if I want to do thin slab casting, probably it has to be done in Tata Steel, Holland. If it is slab casting, it can be done in Jamshedpur also. So therefore, people will not introduce new equipment just because you are giving a solution. That has to be remembered. And then goals will be productivity and quality should be as high as possible. Cost should be as minimum as possible. Now, let me take, in this, for example, once the liquid is there and it comes, first you see continuous casting. And then, it goes to reheating, then hot rolling, then there is the runout table, and then you see it gets coiled, and then you start cold rolling, and the cold rolled material is intercritically annealed, and then the product goes out to the market. So this is the kind of a continuous chain. If all these are connected together, this is known as horizontal integration. But you see, as I said, you start from quantum mechanics and go right up to macro scale. That is vertical integration. For example, just take casting. Here, you require multi-phase CFD flow and thermal modeling, solidification and inclusion dynamics, coupled with thermodynamic and kinetic models, prediction of macro and micro segregation, inclusion distribution, columnar to equiax transition, precipitates, and then thermomechanical processing models for the presence of cracks and bulging. Bulging comes out because of the release of dissolved gases as the temperature goes down, and that leads to a certain degree of bulging. And of course, it can also happen if there is wear and tear in your continuous casting equipment. Some bulging will come because of the larger gap that is developed because of the wear of the equipment. So that also is possible. And then, when it solidifies, some microstructure gets developed. So that means you have to have phase field models. Phase field is nothing but, if I want to put it simply, it assumes that when a liquid becomes a solid, a sharp interface develops. This is a basic assumption which is necessary. Once the thing is assumed that way, it will be possible for you to work out the energy associated with the interface, the volume, and so on. And this leads to the famous equation developed by John Kahn and his associates. Takes you to the Landau-Ginzburg equation for grand potential, as they call it. That is free energy. This is basically free energy minimization concept. And you minimize that, and you will develop the kind of microstructure that is developing. And if you go to reheating, mainly, the temperature has to change, and therefore you require a precipitate dissolution model and grain growth. In hot rolling, there is also shape change of the grains, recrystallization and recovery, and incoming, of course, microstructure can be different from heat to heat, and also segregation could be a problem. In runout table, temperature goes down, cooling is done, and therefore austenite transformed to ferrite, and this will lead to phase change and also microstructure evolution. Phase field methods are very handy here. And then when it comes to cold rolling can be done, analyzed in different ways. Deformation, of course, is there. In addition to that, texture models. Texture models can be done in two ways. One is, the industrial approach where they assume, as the deformation proceeds, the shape of the grains also changes proportionately. So this is the so-called pancaking and pancake approach. On the other hand, one can do it more rigorously through texture analysis. Like what is being done by people like Samajhdar, Ranjit Ray, Satyam Suhas and others. So there you see it is much more difficult to correlate the texture changes with properties. And some new methods are coming here. While talk, a bit later I will talk about it. Crystal plasticity using discrete Fourier transforms. But then, again, these are statistical methods, and fundamentally, for example, to predict for two-phase materials, the mechanical properties from the texture is still a very big challenge. And then, go to intercritical annealing. In intercritical annealing, you have, again, the nucleation of a new phase. And therefore, you see, you will have to, here, of course, as you know, dual phase steel is a mixture of ferrite and martensite. And this, you see, grain size evolution, phase field modeling, and all that will be called for here. And from here, you have to take one step further to predict the mechanical properties. And this is achieved through using of concepts of micromechanics and also yield criteria like Gerson, Vegard, Tetelman, which is a very popular equation which takes into account the effect of stresses, the stress state, and so on. So property predictions can also have to be done. So at the end of the day, the requirement will be either a slab or a sheet which have minimum inclusion and minimum defects. So that is the customer's requirement. But then one has to go through all these things to be able to achieve this. And again, we have to simplify a problem to the maximum extent possible. You should not analyze the problem more than it is necessary. So this is a message I want to convey. So we can do it at the macro level, in which case we can use, of course, if you are lucky and end up with a first order differential equation, you can produce an analytical solution. Otherwise, also you can have numerical solution. And then, you get into finite element methods and computational fluid dynamics. These are macro scale models. And when you go to mesoscopic, mesoscale models, phenomenological, this is what I mentioned about when I was talking about the texture, crystal plasticity, finite element. Here what you do is, that is a whole spectrum. You take a texture of all, infinite variation texture will be there between one grain to the next if you analyze the whole material. You cannot take all of them. So that means you select certain orientation, applying what you know from dislocation theory and crystal plasticity, and select these primary examples and use them statistically in order to predict the property, combining with finite element method. This is the crystal plasticity, FEM. And of course, there is also another method called cellular automata. Cellular automata defines the neighborhood of any particular grain or any particular configuration. Now, if I know how the neighbors are arranged, then, in the initial condition, and if I also know how these conditions are changing as a function of time, then, it will be possible for you to work through with the cellular automata method. When you come to micro scale, of course, you have phenomenology as well as cellular automata. And in addition to that, you have got phase field, which I already explained. That is assuming that when the new phase is forming, it forms as a sharp interface. And then, you can work out using the minimization of free energy concept. Of course, if you are, this has to be done for theoretical purposes at the universities, maybe at the back end of the R&D organizations, but this industry cannot afford. And these are phenomenological, density, dislocation dynamics, molecular dynamics, density functional theory, and Monte Carlo. And Monte Carlo methods. So these are the various methods that are available to you, and you stop at the level of analysis that is needed for your problem. And that means complexity is need-based. Focus has to be mainly on integration across process chain. And here, this is a slide, don't bother about the details. It gives you various kinds of software that are available for different things. You cannot afford to buy all of them anyway. So therefore, you will have to use what you want essentially, and then you have to develop your own product. And again, as I emphasized earlier, you are interested in only developing the more or less accurate value, that is reasonable accuracy. And then this is based on physics and empirical rules that you have evolved, experimental results and so on. Then, what you do is you use, today machine learning is there. In machine learning, you have got methods like transfer learning, which is a variant of deep learning, which in fact, we have been doing that. What you do is you develop an equation for a particular situation. Then you want to see whether it will apply to another similar situation. So what you are doing there is you are extending it. This is transfer learning. So this, is done automatically now in the computer. So therefore, they call it as deep learning or transfer learning and so on. This is basically common sense. But at the same time, you have to remember the rule we always adopt, that extrapolation is dangerous. So that means you have to carefully extend it. And here the computer can be useful because it can try numerous things. From there, try to arrive at what is most reliable kind of extension that is necessary. And now I will, this will be the last part of my lecture where I will give two case studies. One is what we did in collaboration with Birla Copper, which is in Dahej in Gujarat, and Aditya Birla Science and Technology company is which is the whole holistic R&D center for the entire Aditya Birla group. They were also very deeply involved with it. And the data I will not be able to give because they are owned by the company, but the concepts we will be able to give you. Here, for example, is a unique kind of tool or simulation tool, you can call it, for continuous casting, which has been developed for Aditya Birla. This is, for example, what are the inputs you have to give? Caster geometry, including mold and strand, melt temperature of feed to the caster, casting speed, and cooling zones. For example, there will be some water cooling of the slab that is coming out, and also there can be on the as the casting is coming out, there will be vertical guides which are made of copper. This is the copper block, and the top and bottom, as the slab is coming out, is made of steel. So therefore, it is a complex heat transfer problem, and that means copper extracts more quickly than steel. Anisotropic kind of behavior is possible. But then, the problem is simpler in copper than steel because the size of the billet or ingot is much smaller. And therefore, what I talked about as the columnar to equiax transition, that becomes less of a challenge here than what we will have in case of the steel industry. And therefore, you have a thermal model for taking all these into account. And there, you will be able to predict the grain morphology, that is columnar to equiax transition, crack susceptibility, that is, you find out the points where the stress concentration is the highest, and there, the crack susceptibility would be the highest. And then distortion, which can come out of solidification shrinkage, and also thermal gradients, which will also introduce residual stresses. And that means by a proper analysis based on finite element, you will be able to identify the locations which are likely to crack, and also distortion where it is likely to be maximum. And then, in an industrial plant, you cannot have a total inert atmosphere. So the air is there, and therefore surface oxidation cannot be avoided. And this, of course, by understanding the real situation that exists there, you will be able to predict what should be what is likely to be the oxide layer thickness. And in addition to that, the material which we are talking about here is what is called in industry as pitch copper. Pitch copper is copper with about 200 ppm of oxygen. And therefore, as far as inclusion formation is concerned, we are considering only inclusion of copper oxide. So copper, you consider the copper oxygen binary diagram and then find out the eutectic point, and there you see you will be able to work out what is the CO2O distribution in the cast material. And again, you have the porosity has to be predicted. The porosity, how it is done? It is by differential pressure idea. That means, when there is a hole, or, this oxygen and hydrogen. Hydrogen comes usually from the fuel. Oxygen and hydrogen, which is there in the copper, when temperature is lowered and solidification takes place, they get released. So that means there will be some kind of small cavities which will be empty space because the gas has escaped. So now, because of the differential pressure and the thermal gradient which is there also will add to the stresses which are present in the neighborhood, there will be a collapse and this will form the crack. So that means porosity mapping can also be done. So this is a very, it's one of its kind, which is now being used extensively by Aditya Birla Research Center, because it is now easy for them to say what happens if I vary this variable or that variable, and how the microstructure changes and so on. So this is the outcome of a collaboration with Birla Copper and Aditya Birla Science and Technology Center. And here, this is what in a nutshell happens here. That is, you have all the casting parameters given, like the number of holes which are there for circulating water, and then how many of them are there, and water, how it is distributed in the slab so that the cooling is understood clearly. From there, you work out a heat transfer coefficient to fit the data. As I said, data is very important, which only comes from the plant. And then, you put it into the simulating tool which you have got. And there you see, as the process continues, you have more and more data. Therefore, your heat transfer coefficient will get continuously improved. And particularly because it can be done through machine learning, it is not necessary for you to look at every day and see, improve the calculation. It is automatically done. And then the improved values of heat transfer coefficient is continuously given. And then, you give the thermal prediction, which of course, will be compared by some people, in this case at the Science and Technology Center. They will measure the values and compare it with the predictions and see how good they are. This way you will be able to predict the bar temperature after secondary cooling at the primary casting exit, water outlet temperature, belt and dam. That is, dam is what is called the copper block, which I said vertically placed, and belt is the one which conveys the solidifying slab. These temperatures can be predicted, and this of course is the heat transfer coefficient gain. And similarly, porosity, as I said, can be predicted using the pressure differential method, and you will see here that all these areas are very clean. Porosity is only at this place, the extremes are the highest, about 10%. Therefore, as your product is going for rolling, cleaning up will take place, they will disappear. And the rest of the porosity that would be there, they will get well. Similarly, as I said, the CO2O, which is the precipitate that is coming out, how it is distributed is shown here. Here again, you can see the percentage is very small, because after all, the oxygen level is only 200 ppm. So that way you are able to get it, and all these will not create problem in rolling. And again, in this model, you can work out also how the stresses, this is mainly heat thermal gradient as the temperatures are going down, and it is a complex problem involving convection, conduction, and of course at the highest temperatures even radiation. So therefore, by the finite element method, you are able to find out the stresses at different points. These are expressed as ratio of mean principal stress. That means if this red color is here, so that means here the stress is 2.4 times the principal mean stress. So such points are the ones which are likely to crack. And therefore, it will be possible for you to understand the cracking susceptibility also. So this is the thing which was done for Aditya Birla. And now final case is that of Tata Steel. And here, of course, we need two things. One is microalloy steel, where you end up with hot roll coils. And in dual phase steel, you end up with cold roll and intercritically annealed. So that is there. But basically, what are the things which we are able to do? We can leverage the plant data. We go on more and more data we get from the plant. We are able to improve the predictability. And then I will give you an example of design space exploration. That means when I say design space exploration is what happens when I go to temperature of 1150 or whatever it is, and then hold it for a certain number of hours. And then, do that, what happens to the microstructure development and all that. Or I can also say for the whole process, what is happening. They're taking into the process thing. And then with this kind of model, you will be able to get what is the maximum you are putting your equipment to, maximum effort. But the equipment must have certain capability. If it is more than what you are using it for, then you can think of new products. Of course, market should be there. New products within the present capital expenditure. And also, you may need some new products for which the capacity may not be there, which of course again is predicted. And then, it becomes possible for you to decide intelligently on the new investment that you'll have to make. And as far as the plant is concerned, we have to always collect everything. That is product and quality of product and quality data, process parameters, and again, control capabilities, process capabilities, and then, slab quality and grade specific heat transfer data. All these things will, of course, as I said, 1 minute, I'll tell you that. Grade specific data, because you see, the plant has been existing for quite some time. So all these data they will have. Collect all of them, feed it into your model. And then, now comes the machine learning part. Here, you see, you have the manufacturing execution system from where you will be able to collect data, because, nowadays sensors have become cheaper. Because earlier they were expensive, but now you can afford to put sensors in all measurable parts. So therefore, you get a lot of data coming in, sensor data, and then quality data which comes from your customer and your own assessment, and then process data, how much deviation you are making, is it inevitable, can you improve it? All these information, they get going and they continuously improve your physics-based models, empirical models, and also you are continuously recommending to the manufacturing the quality of your recommendation will improve. And at the end of the whole exercise, what you will be able to do is what is known as digital twin. That is, a process is identically reproduced in the computer. In fact, TCS has now become so confident about preparation of the digital twin. At one conference, Dr. Pradeep announced that one of our aim is to produce the digital twin of Professor Padmanabhan. And I don't mind it because I am already 76. So therefore, if they produce it within the next few years, no problem. And here, of course, the applications, synchronous digital twin, that means, you produce the process ideal state and then produce a model which exactly replicates this. And then, it won't be the case throughout the process. So in the plant, from time to time, there will be deviations. So that means you identify the faults and locate them, and then do the root cause analysis and improve the operation. All these, as I said, should be available to the operator by just twiddling knobs, because he will have to do it in real time. And the fault quantification. And once you quantify that, it will be possible for you to once again go back to your ideal digital twin. Okay. So that means online optimal correction becomes possible. And then, you can also predict that way when your asset is likely to fail. And therefore, to avoid that, you can also think in terms of predictive maintenance. Knowledge guided process design becomes possible. So these are all many important tools we have as a result of this approach. This is a simple picture of hot strip HSLA. So that means reheating. Basically, what happens in reheating? So precipitate gets dissolved, austenite grains grow. In rolling, deformation is there. That means the grains get elongated, and austenite recrystallization is there. Of course, when you go to HSLA steel, austenite recrystallization may be there if you have niobium and vanadium and titanium and so on. So therefore, that is where you see it helps you to develop into microstructures which are micron grain. So this is where the HSLA strength comes from. And austenite recrystallization, to what degree it happens, and then precipitates will be there, because if you have titanium and vanadium, naturally carbides will form. And in runout table and coiling, austenite to ferrite transformation is there, and also precipitation is there because the solubility decreases as a function of decrease in temperature. And finally, you have to predict the properties by virtual tensile experiments. And here you have to take solid solution strengthening, strain hardening, and precipitation strengthening. Of course, normally you add it, and therefore you use an additive law. There is no guarantee that it should be additive law, but this is the simplest thing. And if it is not working, you go for higher degrees and adjust it and so on. So property prediction also completely becomes possible. Of course, you have to introduce constants, and the less number of constants you introduce, better it is, because as the saying goes, give me 3 constants, I will fit you a horse. Give me 4 constants, I shall fit you an elephant. So therefore, the fitting constants are to be minimized. So this is where the quality of modeling improves. So we should use the physics to the maximum extent possible, and in the process, we should avoid the fitting constants to the lowest level. And this is the kind of ICME framework. Reheating, then you get a synthetic microstructure, then macroscopic modeling for hot rolling, precipitation comes, and then micro models. And similarly, when it comes to runout table and coiling, you have similar phase transformation, precipitation, and grain growth. And finally, you predict the properties. And this is the kind of, of course, it's in a sense, putting it slightly differently, the curve goes like this. And therefore, you use, as far as the reheating is concerned, the philosophy that is used is semi-empirical models. These were worked out early days by people like Mike Sellers and so on. And now, improved equations are available because more data are available. And the prediction of austenite grain growth is achieved here. And then when it comes to rough rolling and finish rolling, you have cellular automata based microstructure evolution models can be used, because we know as a function of deformation how the shape changes. And also, once you know the composition, it will be also possible for you to predict austenite recrystallization as a function of strain rate, and temperature. And then, when it comes to runout table and cooling, in runout table, only the temperature is brought down. And therefore, and then, it is coiled at a temperature which is convenient. And therefore, you can use the phase field model in order to get the microstructure evolutions and predict the austenite to ferrite transformation, again, as a function of temperature, time, and stored energy. And then you go into, as I said, virtual tensile tests, predict yield stress, ultimate tensile strength, percentage elongation, and so on. This can be done. I will slightly explain it a bit more in the next slide. And this is what I said about this exploring the design space. That is, take a temperature like 1150, and let us say you soak for 100. Then you do 7-stage hot rolling. What happens to the microstructure? You can work out the same way, and then you will also say, as happens to the microstructure of the product, as the number of passes go on increasing. This is the next. And in design space, you can also do this way. For example, for the whole process, supposing I want to understand the runout table and coiling. So I concentrate on this. It starts with this, and by the time I come to the lowest temperature here, microstructure would have developed this. And here again, one thing you have to remember, this is ferrite and martensite. So the dark ones are the martensite. And here you see the ferrite, the grain boundaries are not shown. So this is because of the finite element analysis which is used. Of course, I can make the problem more complicated by bringing in the grain boundaries also. Then in that case, stress discontinuities, velocity discontinuities, all will make your life very complicated. And therefore, the grain size effect is not usually considered. But if you want to take it to an advanced level in the research lab, you are welcome to do so. And testing, here again, you have got what is called WOOF, OOF2. WOOF2 helps you to convert digital data into a microstructure. So therefore, you have this. And then, as I said, you only keep the martensite islands and remove the grain boundaries. So the blue one is the ferrite and this is the martensite. And then, with deformation, the alignment changes. You get this 45-degree orientation, which happens because of shear deformation. And then, as I said, this Gerson-Weygart-Tettelman's equation, for example, which correlates the principal stresses that are operating, the nature of stresses, that is whether it is compressive, tensile, and so on. All these things are taken into account. And then, it will be possible for you to predict the property of yield stress. Yield stress is done in a fairly rigorous way. When it comes to UTS and percentage elongation, still a lot of empirical rules are used, which are experiment based. And this is, of course, what I said, you will have to take into account variations in the plant. And that, you see, I will not go into it in great detail. Here, what you do is, you want a particular input value. Supposing these values are not met, because your source changes, supply source changes, and therefore your input values are different. How do you take into account? So you should know what is the range with which it will change. Then, it will be possible for you to use your model in order to predict the new situations and then, do the corrections. And out of that, you reduce what is called a reduced model or surrogate model, which should be usable in real time so that the plant operator will be able to adjust it quickly to suit the changes in the incoming product. So, here I have spelled out details about what are the inputs in various stages like, reheating, rolling, runout table, coiling, and so on. So this is the way what if situations are considered, and I should know how these things vary, and when they vary, what are the effects. And now having done all this, so there is the most important thing is the human integration, which I talked about at the beginning. The plant, the R&D chap produces the new techniques and methods, and then establishes the validity and generates the knowledge. But then the technology man will have to industrialize it. In other words, he will have to decide what are the points in which, in other words, I cannot be measuring at innumerable places. What are the key steps where I would know the output values so that whether the model is working or not, and whether my process is being done properly or not, so that I can adjust it. So this is the industrialization of tools and workflow. And then develop the methods for that. In other words, if you take, let us say, the copper example, which we talked about, there can only be certain places in the continuous casting plant where you can measure. You cannot put you cannot expect the temperature at an unmeasurable place to be known. So therefore, you identify the points in the practical situation which are measurable and comparable with your theoretical values. So for that, methods for the same, and then you go on validating your data, and then increase the total data that you have, and that way you improve the efficacy of your model, the efficacy, accuracy of your model. And this is also not enough, because a plant, having done that, it has to go down to the plant process engineer. He has to make the design decisions with knowledge input. And as I said, at this level, it should be as simple as possible. It should be by pressing some buttons or twiddling some knobs, making sure that the twin value is reached by your practical value, so that you know that everything is going on. So that means there is design integration, model integration, that means across the scale, as I said, quantum mechanics to continuum mechanics, and then computational integration. That is, you see, today, you can do all these things in a hierarchical way. I do this first, then next, and so on. On the other hand, I can also do it concurrently. That will be time saving. And various domains are there. They have to be interconnected. And today, edge computing is there. So that means even at the edge, you will be able to do without the central server. So therefore, many developments in computer science should be taken advantage of to have the best effects of computer integration. And of course, most important is organizational integration, people integration, and enabling platforms and standards. So platforms and standards more and more have to be brought in for every practical situation, and that will be the most important thing. Here, I would like to give an example. A simple thing like office automation, many years ago, maybe in the 80s, which was introduced in GM, General Motors. GM, when they nearly lost 10 million by office automation, because they didn't do it properly, because the most significant absence was people integration. People were doing things which others didn't understand. So the whole thing was there. It led to a loss of $10 million. So when you go to industry, the losses are enormous. So you have to be careful. This is the final slide. And here, in fact, I talk about casting means I require flow, temperature, solutes, microsegregation, and precipitation. This can be done with ANSYS, Fluent. These are commercial software. And then there is OpenFOAM, which is an open, freely available software, which is available. This can take care of the casting stage. You see, if you are trying to develop something for industry, you should only use software like ANSYS, Fluent, or maybe at the most Abacus and Thermocal, which most of the industries will have. Complicated commercial software, if you introduce, it will make the whole thing more expensive. And the next is reheating. Here you need temperature only, and that will lead to precipitate dissolution and grain size, can be easily handled with ANSYS and Fluent. Hot rolling, temperature, deformation, segregation, grain size. Here ANSYS is there, and the TCS has got a cellular automata tool developed, which is there. And of course, Codaster is again an open source. And runout table, temperature, phase transformation, microsegregation, ANSYS, and of course, TCS has got its own phase field too. And in cold rolling, deformation, and texture, I already talked about how to handle it in different ways, semi-empirical, industrial way, or more rigorously by the new methods of crystal plasticity, finite element combination. This can be done with ANSYS and Codaster. And intercritical annealing, temperature, phase transformation, and recrystallization. For this, TCS has got its own phase field tool. And property prediction, as I said, things like OOF, DS, and MOOS. MOOS, again, this is I think it came from NIST, and therefore, again, an open source. So these are the 3 free softwares which we are using to develop these properties. So this, in a nutshell, is why you go in for finite element. Why you go in for computational materials engineering, why you want to do it in an integrated way, and in what way it benefits, And as I told you, the return on investment is anywhere from 3 to 10 times, and therefore people welcome it. And therefore, I hope I have made it clear why ICME has become important, why it is now being popularized. And in fact, there is a program of Government of India which has been put in the next, there is no 5-year plan anymore. For the program of the next 5 years, they want to create a national physical cyber system for making this possible. So therefore, academics as well as industry can come together and work on real problems rather than taking up some problems which appear in a foreign journal. And if they have done it from 400 to 550, extend it from 550 to 700. So this kind of research should be discouraged, and probably relevant research, which is also technologically and intellectually challenging, that should be attempted. And this brings me to the final line, which again I take from C.V. Sundaram. He always used to say, excellence is not mutually exclusive from relevance. Gandhi was a supreme example. Thank you.
So now we have time to take a few questions. So I would request those who have some question or would like to seek some clarification to raise their hand digitally. Right now I have Professor Raman from NIT Trichy who has expressed interest for asking a question. So Professor Raman, may you unmute yourself and go ahead with your question, please.
Yeah, thank you. It's a very, very highly motivating lecture by Professor Padmanabhan. Sir, I have a question which you may consider to be possibly non-technical. This area of ICME, where dynamic interaction is required between the academia and the industry, what do you foresee as the possibility of faculty, professors setting up companies, for example, to cater to ICME needs in mineral processing, chemical metallurgy, extraction metallurgy, and so on?
Certainly, that is the idea. In fact, one of the things which right now a few of us are working on is to develop a kind of a framework for the Government of India to have the required physical cyber ecosystem in India in order to carry out this research. This, of course, is making sure that the academics start getting interested in this field and are able to interact with industry. And in the process, the whole thing will develop. Out of this, those people who move the fastest, we hope they will set up their own industry. So therefore, not only your question as a possibility arising, but also Government of India wants to facilitate it.
Thank you, Professor. Thanks a lot.
And in fact, right now, I named only a few universities or institutions, but the idea is to make it available to as many as possible. And also industry can also use it and locate it in different regions also if necessary, because travel time can be eliminated. Okay.
Thank you. Thank you.
Thank you.
Is there any other question? Anybody else like to ask any question? So if so, please raise your hand digitally. Yeah, Professor Raja, please go ahead. Unmute yourself and go ahead, please.
Can you hear me?
Hello. Yeah.
Good evening, Professor Padmanabhan. It's a very, very nice and excellent talk, and it's taking a very big perspective, from atom to production, I would say, I think. My question is related to how much in this ICME it depend upon the experimental data as of now, and to make it work. What fraction of the experimental data required to make this ICME successful in the cases what you have illustrated?
Well, you see, point is, as a percentage, it will look low. 10 to 20%, will be from industrial data. But then, we use the concept of adjustable constants. So therefore, if you and I, as PhD guides, would look into it, we will ask our students to do a lot more. But as far as industry is concerned, it is within a narrow band. In other words, if you are producing something, the values will not change as you would have in a theoretical situation. So it will be a narrow band. So these constants which I develop from the data available can be used nicely. Therefore, it is small. But if I want to do it at a fundamental level, then, it will be a lot more. So that is where you see, but unfortunately, there are many equations which cannot be solved even with the fastest computer available. If you want to solve it in, for example, if you see my book of 2001 on phenomenology and mechanics of superplasticity, we would have said that, in thermomechanical processing, temperature set of equations are there. And also there is the deformation equations are there. You cannot solve them simultaneously with the computing power that is available in 2001. So you say stepwise you do it. That is, first you solve for temperature and then, you do for deformation or the other way around. Now you see computer power has increased. Therefore, we can solve both of them together. But then unfortunately, to get a consistent solution which will be valid for both the equations you have developed for temperature as well as for strain is not possible. So that means your theoretical thinking has to improve further also. So therefore, this is the beauty of this whole thing. Of course, Pradeep always says of one thing, ours is a very wonderful profession. We solve a problem and in the process create 10 more problems so that we will continue to be in demand. So that is the way it is going on. But then, our depth of knowledge increases. But we never stop. So to sum up, 10 to 20% as of today, from the industrial point of view, if you look at it academically, the figure will be much more.
That's very nice. 20% is not a very large number as it is to automate it. Thank you very much.
And again, basically one more thing we have to concentrate on is, what are you doing? People measure many irrelevant things. They will report yield strength without telling what is the heat treatment they have given. So these kind of values are completely useless. So therefore, we have got a system within the analysis framework. What we call is hierarchy of data. Of course, we as students know, if it is from Hume Rodriguez group, you can take the data as valid. So like that reputation comes, but now you can do it in a mathematical way.
Thank you.
Thank you, Professor Padmanabhan. I don't see any other hand raised for questions. So may I request Professor Samajtar to conclude this session, please?
So, Professor Padmanabhan, thanks a lot for accepting our invitation. It's an honor, sir. A token of appreciation will be sent by Amartya or Karthik to you in your email. Thank you, Professor Padmanabhan. Dear participants, if there are any further questions, you may write to Amartya or me, and we will forward it definitely to Professor Padmanabhan.
And also, I assure you that there will be a response.
Oh, that is guaranteed. Huh?
Yeah,
as always. Pleasure, sir.
Thank you. Yeah,
Okay.
let me conclude by saying that it was a delightful evening. I am glad, it is nice to talk to people who comprehend things. Half the time we talk to people, it goes over their head. So therefore, to have an enlightened audience itself is a pleasure, number one. Number two is, this was a lecture in memory of Professor C.V. Sundaram. C.V. Sundaram was 16 years older than me. I lost my father at the age of 8. In him, I found a father figure. So it is a great honor for me to have delivered the lecture in his memory. And I thank Samajhdar and Mukhopadhyay to have invited me to give this talk. And it was a very enjoyable evening. I thank all of you. And as I said, Sundaram taught me to believe that one should think beyond the self, beyond the present, beyond this life. So if I want to leave you with a message, I would like to leave with this, because it has enabled me to do whatever little I did in a fairly positive way. And to maintain a positive attitude to life is the most important thing, in my opinion. Thank you.
Thank you, Professor Padmanabhan.
Thank you, Professor Padmanabhan.